Hello, I'm Jack Clark and welcome to my line-by-line analysis of my Python code. I hope that through the course of this demonstration I will show you how the research that I've put in has been used in my code. I thought that I could represent it in a video format with a digital pen rather than with another report, as this would be easier for me to produce and easier for you as my marker to access. So, as we can see, the first two lines of the code simply state the title and who it's written by, me. Then we see line 6 to line 9. Here I import libraries. In Python, I have a few functions that I can do. A library is simply unlocks function. A library is written by someone else and unlocks more functions which I can then use in my code, allowing me to do more adventurous things with my code. So the first library I import is NumPy. This library basically did all the arithmetic stuff in my code, such as cosine, sine, all the maths. Then we see line 7 to 9, I import Matplotlib. This library allowed me to produce the animation at the end of my code, allowing me to view my program and what it had produced. Here we see our first comment, shown by the hashtag. Comments are extremely important in Python, as it shows external people, such as yourself, the thinking at each stage in my code. But it also shows me, should I have a break from the code, what I was thinking at the time I wrote this, making it easier for me to come back and edit it. In this particular comment, I say that I am setting up the figure, the axis and the plot element we want to animate. This references lines 12 to lines 14. Essentially, in these lines, I set up the blank canvas on which I will later animate the pull break. Then we move on to lines 17 and 18 through to 19. Here we have bpos, meaning ball position, bvel, meaning ball velocity or ball speed, and b4, meaning b-force, ball force. In these, each of these has a list within a list within a list. These lists are demonstrated by the square bracket, as so. In each of these square brackets, I have the first list references which ball I'm referencing, n. The second list shows the x and y of either the position, the velocity, or the force. And the final list shows the time step which we are referencing there. As I've just underlined, this comment was probably the most important one throughout the code, as it told me later on how I needed to reference all the input, how I needed to reference my lists. I feel at this stage it's important to mention the structure of my code. I've based my code structure on an Open University document on how to produce mathematical models. In this document it says you should always put the variables at the top, hence why I have. Another advantage of this is it allows you to change them all at the beginning of your code rather than having to go through every line changing each one as they appear. So, here we can see my first two variables in lines 22 to 23. The first one is n, the number of time steps. It's very simple to set a variable. You simply state what you want the letter of the variable to be, in this case n, equals, you set it equal to a number. In my case, 20,001. In terms of how I got this number for the number of time steps, for me, it was just personal preference in this, however long I wanted the simulation to last. I changed this depending on how I want to use the code. With the time step, however, though, this was much more scientifically chosen. I knew that I would want the time step to be very, very, very small. This is because if it was too large, I would see balls interacting in weird ways, and the animation would also appear clunky. For example, the balls would roll into each other, would roll together, then a force would be exerted. However, due to the length of the time step, this force would continue to be exerted until the next time step, where they would then fly off in drastic directions because the force had been generating for the whole time of the time step. Therefore, I knew it needed to be very small. Initially, as I was going through the code, I set this at 1/60 because TVs run at 60 frames a second, so I thought that this would be an okay time step for me to use. However, when I then had finished the code, I returned to this and realized that this was far too large, and through a long, hard process of trial and error, I kept on reducing this and reducing it and reducing it until I reached a value that I thought, using the eye test, showed a pull break well. The next 4 variables are very simple, from lines 27 through to 31. These are simply constants about the balls which govern the physics. The mass of the cue ball, mc, the mass of the other balls, mn, the radius of the cue ball, rc, and the radius of the other balls, rn. I found these values on a pool website online, ordered some pool balls and checked the size in the lab. The readings matched, and so I was happy to go ahead with these figures. These will never change, as the size of the pool balls and mass will never change. The next 3 constants are slightly more interesting, especially this one on line 33, Ks, the spring constant between the balls. I am modelling my pull break and the collisions within it using the spring method. In this, as a collision happens, each ball sort of squashes together, as shown. The overlap which these balls cross determines the force at which they move apart. This spring constant means that references for a specific overlap size, the speed or the force at which which will be produced on the balls, sending them in the directions that they need to go in. Here and here. I started with this value being very small, as I had no idea what to make it. However, when it was this small, the balls actually appeared to sort of ghost through each other. Upon further examination, I noticed that this issue was actually because of the spring constant, so I increased it slightly, and so on and so forth, until the balls appeared to, they did collide and they no longer ghosted through each other. However, they took an age to sort of push apart, and it was almost like sponges colliding. At this stage, I realised that I just needed to keep on increasing this value. I did so until a point which I was happy with, and which in the animation it looked like a collision should. It was very hard to use science to get a specific value of this, because in the real world the balls are not 2-dimensional springs, they are balls. So in this, it was just simply through trial and error that I had to get this value, but I feel quite happy with the value I have got. The next 2 constants, seen in line 34 and 35, add friction into my model. In line 34, this is Kv, frictional constant between the ball and the fabric. In a pool table, there is friction between the balls and the fabric, and I needed to find a way to include this in my model. Thus, I used this value. The way I found this value was by setting up a simple ramp, which I 3D printed, rolling the ball down it at various heights on the ramp, using a ruler behind and obviously time to work out the initial speed of the ball and the final speed of the ball. I thus worked out the frictional value. There are better ways of working out friction. However, during my research, I found that friction is a very complicated thing, and that this was a good enough value for my model. Line 35 is KVC, the frictional constant during a collision. When watching my animation for the first few times, I noticed that balls were not actually losing energy from collisions, but in many gaining it. I realised that this was because I didn't take into account energy loss, such as sound energy, in my model. I could have added this energy loss in my code later on, however, computationally this is very difficult. Instead, I thought I could just add a frictional constant in here of basically the energy that gets lost in a collision. This I made this value 4 times the normal friction, and during using the eye test this seemed to work, so I stuck with this value. I also checked this value in the 2-ball collision, and using the data from comparing my data to data that I worked out the Newtonian method. Using the Newtonian method, the values were similar, and I was thus happy with this frictional constant. This next comment is probably the second most important comment in my code, from lines 37 to 46. Here, I tell myself which number corresponds to which ball. So 0 is n. So n is 0 is the cue ball. 1 to 7 are the red balls. 8 to 14 are the yellow balls, and 15 is the black ball. However, I found that once I'd run through the simulation about 10 times, I knew what each of these balls corresponded to. It also reminded me here on 40 and 45 that in the second list of the ball position, when I'm talking about the if I put a 0, I'm talking about the ball's x direction, i.e. left and right. If I put a 1, I'm talking about the ball's y position, i.e. uppy downy. This next section of my code, from lines 50 onwards, looks very confusing and long. However, it really isn't. Here, I simply set the initial positions of all the of all the balls. I use the same source that I used to find the ball radius to find where the balls go. However, all this source told me this time was what's known as the foot spot, or the spot in which the black ball sits. Therefore, using my knowledge of how the balls are racked up, and simple maths, I worked out where all the balls should be in relation to this black ball. I thus put in all the values, and my balls were racked up and ready to go. Here, from lines 80 through to 96, we see me setting the final positions of the balls. This is the same process that I explained previously. In lines 100 and 101, this is actually setting the ball velocity, not the ball speed. Here we see this is just for the cue ball, as obviously this is the only one that is moving at the beginning of a break. Here in line 100 we see a 0. This tells us, as previously explained, that this is the speed of the ball in the x direction, and as this is positive 24,000, it is heading in the right direction towards the pack. Here in lines 101 we see a 1. This tells us that this velocity is referring to the ball's velocity in the y direction. Obviously here we see this is a 0, so this tells us that for this particular simulation the ball was travelling at 24,000 millimeters a second in a straight line towards the right. Then we enter the main loop. In the main loop, I calculated the speeds of the balls and then the forces of the balls after a collision, the effect of this on the speed, the effect of this on the acceleration, and so on and so forth. This included collisions between balls, collisions between pockets, collisions between cushions, and any other collision that happens on a pool table. It took me a long time to work my way through. This main loop was what took the bulk of the time programming. It was very complicated, and through a process of trial and error, I had to improve it gradually and until I ended up with a working model. So that is what for I in range. This simply sets up the main loop. It tells us that while just run it n number of time steps. A time step is simply all the time is broken into little time steps. Each time we go through the main loop, we proceed one time step, and one chunk of time is proceeded. Then in line 106, we see print I. This simply means, this is completely arbitrary. It doesn't help the code at all. It was simply used for myself to help with the debugging process. I used prints throughout my code, as if something wasn't working, I would print a specific value at a stage to see if that was the bit that wasn't working. So you may see prints later on commented out. I won't make a reference to them there. If they're commented out, it was part of the debugging process. It now no longer prints. In this, the reason this print is still in is it simply tells me that the computer hasn't crashed while running the simulation. It prints 1, 2, 3, 4, 5, 6 all the way on until all the time steps have been run through that I wanted to do that simulation. Say it went 1, 2, 3, 4, stopped, didn't carry on, I would know that the computer had crashed and that I would need to reset the simulation rather than waiting there for ages and then nothing happened because the computer's crashed. I then have for J in range, this sets up a loop inside the loop. You'll see this happen a lot as we continue on with the code. This basically just means consider all the balls. Finally, I then have lines 108 and 109. Fx is 0, Fy is 0. This simply sets the total force on each ball in 0 in each direction, so that at the start of every new time step, the force from the previous time step is not carried forward, thus affecting results. Having run through every ball, we then needed to run through every ball's interactions with another ball. This is for K in range 16. So for example, we took the cue ball, and then we needed to check whether it collided with ball 1, yes, ball 2, no, ball 3, yes, and so on and so forth, until we had every ball checking collisions with every other ball. The next lines of code on 114 and 115 tell us that when a ball is spotted in my simulation, it is sent miles away. This code says if it is sent if the balls are miles away, leave them alone and don't move on. This is because initially, as I was potting balls, or as balls were potted, they a couple of seconds later came flying back on because they'd had a collision off the screen and came flying back on. So I needed to prevent this happening. Thus, later on in the code, you'll see they're sent away. Here, when they are sent away, they're left alone. Then we move on to calculating collisions between balls, as the comment says. So in line 119, if J is not equal to K, that's what that little bit means. This is basically saying if the J ball that we're on if it doesn't equal the K ball, then do this bit. Because if the J and the K ball are the same ball, obviously that's the same ball and a ball can't collide with itself. So we wanted to avoid that happening. The next bit of the code that you'll see here that I'm circling now is it's all commented out. Now, this is because this code didn't work. Initially, this bit of code, or in an earlier version, this bit of code was in my simulation, and I noticed that the balls were acting a bit strangely, and that the balls, sometimes they were colliding as you'd expect, but sometimes they were colliding in weird ways, sort of ghosting through each other, going at weird angles. I wasn't really sure what was happening, so I decided that this part of the code was the issue through different bits of trial and error, and I brought the problem to this angle. I thus rewrote the code, which I'll explain to you in a moment, but I thought that I should leave this in as a demonstration of the trial and error work that went on throughout the constant production of the code. This next section of my code, from lines 1 to deleted, as it is now commented out and serves no purpose. This was my old way of calculating the angle of a collision, and I have since created a new version which works better. This can be seen below, which I shall explain in a moment. I commented out sections of code when I realised they weren't working, so that if I was wrong and that bit was actually okay, I hadn't deleted that code. I still had a spare copy of it, so if the new version was actually worse or messed up the code in a different way, I could quickly delete that and go back to my old code. This next section of my code, from line 131 all the way down to line 152, calculates the angle of the collision. You'd hope that this would be quite a simple process and wouldn't take too much time or too much line space. However, this is not the case. Instead, as you can see, it took up a lot of line and it took up a heck of a lot of time. For each angle, there are 4 cases it can be: either up, down, left, or right. Therefore, sort of the compass directions, for want of a better word. And then there are the 4 between these. So this section here, this region here, this region here, or this region here. Now, when it is either going up or down, obviously the x sort of angle direction is 0. Now, this causes a divide by 0 error. This causes the whole program to mess up. So I had to address this one in its own sort of little block of code here. And the same with the left or right. If it was only going left or right, then obviously the y is 0. This would again cause a divide by 0 error, causing the program to mess up. So again, I addressed that in its own little section here. This left each of the 4 other sections. So if we take the first if statement here in line 142 and 143, this addresses this little section over here. So if the ball is going in that section, I use a complicated maths equation picked out from the A-level maths textbook, which I've based a lot of my research on, a lot of my project on. And it uses this equation to work out where in that sort of sector the ball will go. Note the use of np.arctan. This is a use of numpy. This is why I had to import numpy at the beginning of my code. This next section of my code, line 157 through to line 160, defines colrad. Now this is the collision radius. This is if the 2 balls in the collision are touching, like so, the distance between their centre of masses. That little distance I've just popped on here, this is colrad. Now, this the reason I can't just define this distance is because obviously the cue ball and another ball have a different colrad to 2 object balls, as the balls have different radii. Then in line 162, I define the ball set. This is the distance between the 2 centre of masses of the ball, regardless of whether they touch or not. This here, B sep. Ball separation. Obviously, if the ball sep is smaller than the colrad, as I say here in line 164, the balls are overlapping and thus a collision needs to be registered. I therefore use GCSE Hooke's law physics stuff to find out what this force is in both the x and y direction, and use an and equals sign to add this to the original force. In the next section of the code, you can see another commented out section. I think by now you're seeing how frequent these are, showing that every time that I encountered an issue, I had to comment it out, go away, read Google, read the book, see if there was any solution to my problem, come back and rewrite it. This was a very arduous process and I had to do it over and over, and I think that you're now getting an understanding of how long this took me. However, I think that this is a really good example of this process and shows how much I developed during the course of the project. As if we look here, this section of code and the commented out section actually attempt to address the same issue, but the real one that I've gone ahead and used because it's correct actually uses fewer lines than the initial one. And this shows that that through the course of the project I have developed so that I can now use fewer lines and get something right rather than using more lines and still not have a perfect solution. In this next section of the code, from lines 186 through to 203, you can see that I calculate any collisions between balls and the cushions. I do this using an if-else loop or structure. This means that the first if is if the ball isn't a cue ball. So I calculate any ball on the table. If it comes into contact with a cushion the same way that I calculated the collision with the other balls. However, with it being a cushion, obviously there's pockets in the cushion, so I needed to use specific values, such as here and here. I found these values from the same site that I found the foot spot and the ball radius and mass. So I thus calculated collisions with the cushions and added that to the total force. Again, you can see that I've used the else here because the cue ball radius, as mentioned, is different to the other ball radius, and thus I couldn't just use a generic radius. I had to make it specific for each one. The next section of my code is adding friction into my model. This is crucial to my model and can be seen in lines 207 through to 212. In my model, friction was a huge moment because before this, the model wasn't really working as it should. Balls were moving far too fast and I was having issues, especially with higher speeds. Until I added friction, I thought there was quite a strong possibility that I wouldn't actually be able to model the pull brakes and I would fail my task. However, friction ended up being my hero and sorted everything out. Through my research, especially of the Open University book, I noticed that in physics there are two ways of modelling friction. Either F equals minus K times V, obviously minus because it's in the other direction to the velocity, or F equals minus K times V squared. Again, minus because it's in the opposite direction to the velocity. Now, the V squared approach has the advantage of it counteracts higher speeds a lot, and the higher speeds were what were causing me issues in my project, and so thus having a big impact on those is what I wanted at the stage of the development that I added friction in, and so I went with this approach. However, obviously when you square a number, you negate the minus sign, so minus 1 squared equals 1. Now, I didn't want this, of course, I wanted to include the minus sign. So what I used was the absolute function, as can be seen here, absolute. Now, the absolute function, it negates the minus sign of the second one. So we end up with friction is minus K times V times abs V. So what this does is if it was minus 1 times 1, it would keep as minus 1. And this is obviously what I want. As you can see, I have an if-else structure again. This is because the first if is if the force is 0. This would imply that no collision is occurring, and thus I use the value of friction with just the ball and the tablecloth. However, the else would imply that there is a force and thus there is a collision, and so I use the KVC. This is the frictional constant where there is a collision happening. At the beginning of this section of the code, in lines 214 and 215, you can see B4 j0.append with fx and then with fy. Now this here, having calculated the force using the balls, the cushions, the friction, I finally have the total force on the balls for the time step. I thus append it or add it to the last element of the list, and thus I have permanently stored that force for later use. In fact, I use this force to calculate the acceleration. Again, as I reset the forces at the beginning of that section, I reset the accelerations here again in 2, 2, 0 and 2, 1, 1. I then again have to use another if-else structure, because just as the cue ball and other balls have a different radius, they also have a different mass. I then use F equals ma, Newton's second law, to calculate the acceleration on each ball in this time step. I then use this acceleration and the Suvat equations to calculate the speed at the next time step. So again you can see another if-else structure. This time the if refers to if the ball is off the table, make the speed 0. Whereas else, if the ball therefore is on the table, use the Suvat equations and the previously worked out acceleration to calculate the velocity or speed in the both x and then y direction. I then use these speeds to calculate the new position of the cue ball and thus of all the balls, and thus the position of the balls at the beginning of the next time step. I initially did this just using Suvat equations. However, I found that the position of the ball was not that accurate and balls were still flying around. So I then decided to use a more accurate method by taking average of the speed at the beginning of the time step and the speed at the end of the time step and using that as my speed, and thus I got a more accurate position. At this stage I had calculated the speed and the position for the ball at the beginning of the next new time step, and this time step was thus complete. Thus the main loop ended. So here in 253 to 256, I don't 3, 4, 6, I am simply repeating the process I've explained to you of going through and giving each line data. You can then see in 350 the return. This tells us that the animation function has now completely finished, and that I can now set about all the animation data is there, and I can now set about making the animation. This is exactly what I do on line 354. I make the animation. Again, I took this directly from the Matplotlib example with all the comments to try and help me give me an understanding. The only thing I changed here was the frames, and I changed this for every animation I produced, basically until I got one that I was happy with. Again, as I changed this, as I changed the number of time steps, and I always kept those proportionate. So at this stage, I had an animation produced, but still no way of viewing it. So I needed to save it somewhere. However, in my environment, Anaconda, I was unable to do this directly. So I had to download FFmpeg. This allowed me to produce an MP4 file, and thus allowed me to view the animation. I downloaded this using the tutorial on the Matplotlib website. So there you can see on line 362, I do anim save. This produces a basic underscore animation.mp4 file stored in the same folder that this code itself is stored in. I can go click on it and view it. At this stage, my program is completely finished. I just thought I should mention that obviously through this run through, I have spoken about many structures and obviously many basic programming techniques. I learnt these from a number of sources,